Bueno, yo creo que podemos empezar, ¿no? Y ver si más, see if more people come later. Well, I guess judging from the experience of the previous days, people start coming sort of 20, 25 minutes into the lecture. So, okay. So last time was we were discussing the problem of passing to the limit as the ratio between the thickness and some overall length of an elastic structure goes to 0, right? So so I started with just a rectangle, and then I considered the scalar problem, and then discussed a bit the problem of elasticity, linearized elasticity, on a rectangle where the coefficients in the equations of linearized elasticity represent a homogeneous and isotropic medium. Right, and then I also talked a bit about the case when we have a net. That's what, as Zhikov and Pastukhova call this, or network, if you like. So, of well, a structure. Maybe I should take this a bit longer to kind of underline the fact that in order for this asymptotic analysis to be valid, one must make sure that the length. Okay, so well, these parts of the structure, these strips of which the structure consists, have some lengths, right? L1, L2, L3, L4, L5, L6, and so on, and some thicknesses, right? And we should be able to write equations of elasticity in the form, in order for the analysis to be valid, we should be able to write them in the form in this form. With the dependence on some parameter h, which represents h is the ratio of the thickness of one of this L1 over L1, but we assuming that well, L I over Lj are bounded below and above by some positive numbers, some fixed positive number, in fact, uniformly in I and j, right? So assume that there exists a C such that these bounds hold for all I and j, and the same with the thicknesses L2, L3, and so on. So okay, so if these conditions hold, then the equation can be written in the form that we discussed, with the dependence of these coefficients only on one parameter, h. F is the spatial density of of applied forces. Well, we kind of assume that the forces are distributed continuously over over some region in which this body is situated, this structure is situated. So, so that the force on a subregion, if omega is contained in our domain omega, then the force that is acting, the external force that is acting on this so force acting on omega is given by the integral of f over omega. That's what this f is a vector, right? So f is f1, f2, f3. Here in Mexico, do they use this notation or this for a vector? The upper one, this one, yes. In Russia they do as well. So yeah. Right. Yeah. U's are the displacements of the points of the medium. And well, yes. So I mean, in principle, mathematically, you can say I will take any point x, either in the body or outside the body, even doesn't matter. And the displacements here are going to be 0. The displacements for points x that do belong to the body will be represented by some non-zero in general. Well, or if the body is not deforming at that point, it will also be 0. So, but actually, if you start with the original sort of formulation of elasticity, then U that is written here, that appears here in this equation, is the scaled displacement. So the actual displacement, the actual displacement, I put actual, well, maybe I shouldn't put it in quotes. It is the actual displacement that we observe or hope to describe with these equations is maybe I will call it epsilon. I think I called it epsilon. This parameter is some parameter epsilon times u. And, well, strictly speaking, it's going to be some non-dimensional parameter epsilon times u. All quantities here are non-dimensional. So actually, this is the force acting on omega is given by this times some coefficient. Well, maybe I will call it beta or something, because I have had gamma, alpha, c already. So here beta. So here f is non-dimensional. This f is non-dimensional. And beta. Okay, so beta has such dimensions that this has the dimensions of a force. Yeah. So you can work it out for yourself what this should be. I mean, right? So in this equation, in the mathematical, in the end, in the equation which you analyze, all quantities are non-dimensional, and so the actual displacement is. So if this is some beta 1, then there is some beta 2 here, such that u is non-dimensional. Epsilon is a non-dimensional small parameter. and beta 2 is such that this object has dimensions of a length, of distance, yes. So, but beta 2 is just fixed scaling coefficient, like similar to this. These are, you see, these are just scaling coefficients that are not small or large, but they are all non-dimensional. And this is non-dimensional. But epsilon is non-dimensional and small. So so there is an implicit assumption here in this formulation that you have passed to the limit first, as implicit assumption is that you have passed to the limit first as epsilon goes to 0. The implicit assumption is that first epsilon goes to 0, and then we are looking at this problem and make h go to 0. So an interesting question is what happens when you reverse the order, when you pass to the limit at the same time. So you take this structure, you consider it to be thin, so h, this ratio is small. Epsilon, the small parameter, represents, well, epsilon is something like essentially, so, well, from here it follows that epsilon is actually, for example, you could think of epsilon as being the actual displacement, which we assume to be small, displacement, divided by some fixed length, L1, for example. So, and the assumption, the implicit assumption in this theory is that we are considering small displacement. So the actual displacement is so small that we can introduce this parameter and consider it to be small. Well, of course, it has to be small in relation to some macroscopic size. I chose L1, but in view of these bounds, any of these can be chosen. Any of capital L's can be chosen, but not small L's, because small L's will all go to 0. There are these bounds plus h, which is a ratio of small l to capital L, goes to 0 eventually. So, well, maybe I should not call this an exercise. I think this can be the subject of a big investigation. And there are indeed some answers to this already. Well, there is a work that tells you what happens when first h goes to 0 and then epsilon goes to 0. But of course, well, if epsilon, well, there is a work that tells you what happens when h goes to 0 and epsilon is fixed. First of all, that's the case of non-linearly elastic rods or non-linearly elastic structures. Here they're strips, right? And this is a very recent work in nonlinear elasticity by well, there is a famous paper by Frieseke, James, and Müller, where there is very it's an elegant piece of analysis using the rigidity theorem, so-called rigidity theorem, that shows that when gradients when the gradient field, when a given gradient field in L2 is close to the group of rotations in the L2 sense, then there is actually only one rotation. There is a rotation, not only one, but there is a rotation. You can find a rotation, a fixed one, such that this gradient field is close to that particular rotation in the L2 sense. And using that, you can actually represent. You can see a rod or a strip which is bent to a finite amount, as a you can split it into little cubes and follow how the cubes deform, and find sort of effective equations, and those are, well, sort of partially linearized equations, but they are not equations of linearized elasticity, of course, that you get when epsilon is fixed and h goes to 0. So the question of what happens when both epsilon and h go to 0 has not been fully analyzed. It has not been well, I would say that there isn't much to that end. In fact, maybe if I think a little bit, I will find some 2 or 3 individual works where there is some indication of what is happening in that regime. But it's an interesting thing to look at. So when epsilon and h both go to 0 at the same time, so you need to start. But this is the subject of a different kind of analysis to what we have been discussing here, because you would need to start with equations of nonlinear elasticity. Well, I almost didn't talk about that. Right, and likewise, what limiting structure you're gonna get then is a very interesting question by itself. What conditions here? What problem? What is the effective problem? The limit problem as h goes to 0 at the same time as the passage from nonlinear to linear elasticity is done. Right. So okay. So, but I was gonna talk a little bit today about a formulation of the limit problem based on from the perspective of well, using the tools of measure theory, right? So you can actually, I already mentioned using the opportunity of answering your question, I already mentioned that you can think of this whole problem as being set up in the domain omega that contains your body. Well, in the previous 2 lectures, I took the view that that when we write this equation, we kind of solve it. What we do is we solve it in the strong sense, in well, in the structure, and then impose some boundary conditions on the boundary, right? Of course, I also mentioned the weak formulation, which is sort of half step to what I'm about to say now. So in the weak formulation, you can incorporate the boundary conditions as well, and you don't need as much regularity for the solution. And also it has all the structure that allows you to, these weak formulations, they have all the structure that allow you to prove existence and uniqueness of solutions, right? But you can go kind of one step further in the way of embedding this into a general framework, into a more general framework, and think of the corresponding weak formulation. So remember, the weak formulation was this, something like this. It was the integral of C UKL phi phi j I was the integral of fj phi j, right? This throughout here we assume summation with respect to repeated indices. So I, j, j, k, k, l, l, and here j, j, right? So this is just a one identity, one equation, but we take an arbitrary function phi here. So in the end, you have an infinite set of equations for all phi in the space H. That is a kind of energy space for the problem. I used the word Sobolev spaces a lot until I realized that then it turned out at the end of the last lecture that not everyone knew what Sobolev spaces were. But when you think of phi as a test when you take the test function phi here, you only need to worry about you can only take you may only take I mean you may restrict ourselves to taking just smooth, infinitely differentiable, if you like, functions. Of course, here you don't need as much smoothness as infinite differentiability, but you could take as smooth as infinitely differentiable, such that, say, if you have a Dirichlet condition somewhere on the boundary, then your functions are zero in the vicinity of that part of the boundary. But then this Sobolev space, this H, where actually phi naturally reside, like the solutions U, is obtained by the process of closure, by closing the set of smooth functions with respect to the energy norm, the norm that is has got to do with the size of the gradients, functions and gradients with respect to the L2 norm, right? So that's what the Sobolev space is. But I don't think. Well, I'm a bit ambivalent about starting to talk about Sobolev spaces now, but that's what it is essentially, right? And it's all that you need to in order to understand how it works, I think. So you basically just say that the norm in the space H is something like the norm of the function plus the norm of the gradient in L2. Gradient, right? So something like this. Now, but here we still put Lebesgue measure and we integrate over this structure. Maybe I should give it some name. Maybe S. Well, we call it. Actually, I called it omega H, didn't I? I called it omega H. Well, I'll continue calling it omega H here, even though I have this large set omega that contains it. So, but so maybe, yeah, let's leave it like this. So then here the integral is over omega H. But you could also write this. You could also write this as an integral over omega with respect to the measure mu with the support on the structure. So you could introduce a measure which for a given set omega, well, that's very handy that omega is here, little omega. So the measure mu of the set, so consider mu such that mu of a set omega is the Lebesgue measure of the intersection of omega with the structure. So the measure of a set omega here outside your structure is 0, even though its actual Lebesgue measure is not 0. The measure of a set which is contained fully in the structure is the Lebesgue measure, and if you have something partial, then you only measure the part that is in the set. Maybe in order for this to be well, I guess we can leave it like this. You could normalize it. You could make sure that sets of Lebesgue measure 1 have measure mu 1 as well by normalizing, by dividing by the Lebesgue measure of omega. But well, it doesn't matter at this stage whether if you don't do that. So you could write now this formulation in this form, where you integrate over this domain omega that contains your structure. And you can ask, so, and now of course the measure mu depends on h, right? And well, you can think instead of the L2 spaces with respect to the Lebesgue measure, you can think about L2 spaces with respect to the measure mu h. Well, and now it's a sequence of measures. They depend on h. So now you look at the L2 spaces. Well, let's say L2 in R2 in this case, with respect to this measure mu h that is describing the structure. So, and in this way, you can kind of, well, you can describe a more general class of objects than the one that we have just discussed. So here in this framework, you, at the end of the day, you don't really care what your body is like. You just need to say what measure you are describing, what the measure is, right? And you could look at other singular structures. This is the advantage of this approach, of this formulation. So now mu h is mu h is scaled. Well, mu h, okay, appropriately scaled, of course. Appropriately scaled with h could represent more general singular structures. For example, something like this, right? You could have a plate and some rod attached to it, right? Have something like this, which, if you used the framework that we discussed up to now, you can still treat it using the same ideas as before. You basically need to consider equations on the plate, then equations in the rod, the equations of elasticity. Solve them far away from this junction point. So solve equations of elasticity asymptotically here, then far away from the junction point here, and then you would need to tackle the problem of matching, of asymptotic matching, something that we have not discussed and something that is contained in the analysis of Zhikov and Pastukhov, for example, where we talk about the junction points between different net components, right? Those conditions at the junctions I was talking about, where you eventually say that in the limit the functions have to be continuous at the point and the sum of the derivatives is 0. So how you obtain those effective conditions at the junction points, right? So here you will also have some effective. So this is going to be as h goes to 0, and here we assume that we pass to the limit again as epsilon goes to 0 for small displacements. This is going to converge to something like this, right? To an infinitely thin plate. So there will be equations. This is essentially a subset of R2, some kind of omega 1, which is a subset of R2, and then there is this omega 2, which is a subset of R1, So you have a function that solves some probably fourth order equations, because that's the kind of equation that describes plates. So biharmonic equation in R2 here, then you would have some you know, the kind of equations that we wrote down last time. So for one component it's fourth order, for another component it's second order here. Here, by the way, there will also be different equations for different components, right? So for the two components that lie in the plane, these are going to be equations of second order, the membrane equations, and for the component out of plane, it's going to be fourth order, a fourth order equation. And then the question is how do you glue those together here? What are the physically correct conditions at that point? And you don't need to use this framework. You could just look at a specific problem that, say, comes from some applied context, and just solve it this way, right? So you solve it here, solve it there, then do the asymptotic matching. But this approach is not genuine. I mean, it has a kind of ad hoc element to it, in the sense that you will only prove mathematically what the answer is like for a specific geometry. And here you can incorporate any kind of geometry into this measure mu h. So the works where answers for these particular setups have been, were obtained appeared not so long ago. This is the subject of sort of 80s and 90s by some people like Vladimir Mazia and Sergei Nazarov and their colleagues, who have studied a lot of such problems in singular structures. Right? There is a famous book about this, the asymptotic analysis of elliptic problems for singular structures. And actually, that book is just the beginning. Then there is another one where they actually tackle the problems of elasticity and all these systems of rods and plates and junctions. But all these can be embedded into a framework where you have a measure mu h, which simply represents the fact that quantifies the idea that when you take a subset of R3, a set in R3, then the measure should be the actual Lebesgue measure of the intersection of that set with your body, right? With the structure. Right. So. Okay, so I wanted to talk a little bit about the Sobolev spaces that appear in problems with singular structures. Okay. And also problems of homogenization. Well, Shane is giving a nice introduction to homogenization using the from the perspective of waves, right? So maybe I'll mention a little bit how the problems of homogenization can be looked at in the context of thin and singular structures. Right. So if we the case of homogenization the case of the setting of homogenization is the one where you have yet another small parameter, right? In addition to the other two that we have just discussed. And now I realize that I shouldn't have used the letter epsilon for the small parameter representing the passage to the limit from the nonlinear elasticity to linearized elasticity. Should have called it delta or something like that, because traditionally in homogenization you use a small parameter epsilon, right? Okay, so I'll simply not mention that other parameter epsilon now, and we'll be calling this small epsilon in homogenization the one that represents the period in the structure. So if I start with this equation, well, it can be you can think of it the way you like. So you could think of this as a scalar equation, or like sort of diffusion, right? Diffusion, or you can think of this as a vector equation, and then this is going to be, say, elasticity. In the case of elasticity, A is a fourth order tensor that we called C, and U is the displacement. This gradient is a matrix. So you take the gradient of each component of the displacement. So then when you take the product of this tensor, fourth order tensor, and the matrix, you have a matrix, and then the divergence is taken row-wise, and you get a vector. So until I actually said anything about, I mean, I don't need to be specific about whether U and F are scalars or vectors. Or you can think of a diffusion equation, and U is a scalar, this is a vector, this is a matrix. Matrix times vector gives you a vector, then you take divergence, you get a scalar, right? So, right, and this is the feature, the dependence on the small parameter in this way is the feature of the problem that corresponds to the word homogenization somehow. Although it's not completely right, I shouldn't, I should, homogenization is the actual process, or rather the idea of replacing the medium with the small parameter epsilon like this by another equation, or representing another medium, or it can be even not a medium that exists in nature. So some limiting equation. So in some sense you replace this by some kind of limiting equation that I'm just going to call A hom, U equals F, something like this. It may even happen that these functions are no longer U and F. They are some kind of limits. U, which depends on epsilon, converges in some sense to this U, and F, which is also a function of epsilon in general, converges to this function capital F. So, well, of course, this is too vague. You will say there are many ways of just replacing. What is the criterion for replacing? When do you say that you have succeeded in what you are trying to do? And then the question is, well, then you realize that I haven't described what we're expecting, right? So what do we expect when we start with a medium with a kind of medium with some periodic dependence of the coefficients on a parameter epsilon, right? So this is epsilon. So A are one periodic, or rather, well, they're periodic with respect to the sort of unit cell, right? Unit cell Q which is well, this cube. So in d dimensions, it's just a unit cube, let's say. So that is a of y plus ej equals a of y for all y and for all j, in all directions, right? So the properties of the medium periodically repeat as you go from one cell to the next. And then you substitute this variable x over epsilon instead of y, and you see that while omega is fixed, so here I have some equation in omega plus some boundary conditions on the boundary of omega. While the equation is fixed, while the omega is fixed, the coefficients of the equation make vary in such a way that the medium becomes more and more heterogeneous, right? So, for example, if these were elastic parameters, we would think of a very heterogeneous elastic body, right? The properties within the medium actually vary rapidly. But what we don't know at this point is what the solution behaves like. The solution, you take a slab of some metal or rubber, right, with some periodic inclusions, and you would like to understand what to the leading order what the solution to a boundary value problem behaves. So what would we expect? What would we expect as epsilon goes to 0? What sort of intuition do you have about? What sort of simpler equation would you be looking for? The equation where you don't have epsilon anymore, right? Because as epsilon goes to 0, you kind of see that the medium becomes more and more heterogeneous, but the level of heterogeneity becomes so fine that the solution to the problem, actually, it's, now I'm thinking about it, it's not maybe it's not such a straightforward thing to explain. I usually give this example of this analogy when you have a very heterogeneous structure and you move further and further away from it, then it looks more and more homogeneous. But this is a bit of a lame analogy, I think, in this case, because what you really want to understand is what the field within that structure behaves like, not the structure itself. You do expect that the field will behave in the same way within that structure. It will behave, the solution U, will behave in the way that it should behave in a structure, in a homogeneous structure, that is similar to the one that to the heterogeneous structure you are looking at. But it's not obvious why it should be so right away. You kind of see that by writing a few lines of asymptotic analysis, or using the kind of argument that Shane is presenting, using the idea of the language of wave propagation, right? Basically, but this is, well, this is just I guess this is just what happens. So it turns out that the solutions U epsilon converge in the sense of the energy norm, which is the energy attached, which is the kind of convergence that is naturally attached to our problem. So at least the actually the convergence. So the solutions to this problem converge at least in the L2 sense, right? They converge to some function U. So solutions U epsilon behave like this, look like this, and this kind of envelope, which I call capital U, right here. This is what we're looking for. And this envelope solves an equation of the same type under the condition that so assuming that A this matrix or tensor is positive definite. Well, for all xi here, if A is a tensor, then xi is a matrix, and if A is a matrix, then xi is a vector. This condition can be somewhat relaxed as well. You can assume strong ellipticity rather than uniform ellipticity like this. I think Shane assumed strong ellipticity in his discussion. So for all new, the existing, right, for some new. Okay, so assuming that this uniform ellipticity condition is satisfied, then U epsilon converge in the strong L2 sense to a function U, and weakly in H1 as well. And for those of you who know that what H1 is, the Sobolev space, this will be clear. For those who don't, well, it's just some kind of natural convergence associated with the equation and its weak formulation, right? And H1 is the energy norm that I talked about a few minutes ago, where you take small functions and close them with respect to the L2 norm of the functions and their gradients. To a function of the convergence is to a function U that solves an equation with constant coefficients, A home. And these are the coefficients that feature in Shane's lectures as those obtained from the analysis of waves. It's exactly those coefficients. So and these are the coefficients that represent that homogeneous media that we want our medium to think of as behaving like when we move further and further away from this medium, and it looks more and more homogeneous, in fact, right? So so the process, the analysis of this the asymptotic analysis of the sequence of solutions, or the asymptotic analysis of, in the wave context, of the waves propagating through the medium when epsilon is small. This process is the one that you would refer to as homogenization, and the only justification for the actual word homogenization is that you kind of anticipate that the solutions, the limit function will satisfy an equation with homogeneous constant coefficients, right? So that's where the word homogenization comes from. But the more you study these things, the less you like the word. I mean, I personally feel a bit uneasy about this word now. It leads to almost offensive claims that what we do is homogenize, right? We homogenize, but we don't homogenize. We try to understand how the media behave. That's what we do. We don't actually homogenize them. The behavior is there. We just try to understand it. Okay, I have run out of time now. So I I'll just say that in the homogenization context and in relation to the language that Shane is using, it would be very interesting to say, and that could be your exercise, maybe I don't know if Shane will agree with me or not, is to think about his approach in the context of formulations with respect to measures on singular structures, singular measures, right? So, of course, he has been giving, as a matter of introduction, this already. I mean, at the level of ideas, this is sufficient to assume that this that the medium that you are describing is continuous in the full sense of this word, in the sense that you don't have any singular structures in it, right? So there are no defects or places where you would not, where using just the Lebesgue measure in the weak formulation would not suffice, right? So you would just write, first of all, this equation in the weak sense, with the one that I have written several times, and this would be the sense in which you understand the solution. You have the Lebesgue measure here, integral f phi dx, and then you would, so for all phi h, and then you would in the equilibrium context you analyze solutions to this equation, or in the wave, for waves in the wave context, you are looking at solutions of the full wave equation, which can also be written in the weak sense, or to the reduced wave equation, the equation with the eigenvalue problem, right? So you could look at solutions to the eigenvalue problem. So lambda u phi, and ask the question about how the eigenvalues that now depend on epsilon behave, and u epsilon, the eigenfunctions, what the behavior of eigenfunctions is. In fact, this is for a bounded domain omega. This is the context of vibrations, really, rather than waves. When you think about waves propagating through the medium, you need to have outlets to infinity, right? So you need to have waves that come from somewhere and go, again, this get scattered, go away to infinity somewhere. Or maybe, unless you think of some surface waves that propagate along the boundary, this is another exciting subject here, right? So, but the question that I would like to pose to think about is what, or maybe we can discuss it after at the end of our meeting. What say this process of homogenization, what the corresponding asymptotic analysis, and what the version of this analysis using the language of waves would be if you consider the singular structure. So if the domain omega, if your medium, the medium that you are describing, is not described by a measure, by the Lebesgue measure, but rather by a measure that contains, well, it could still be a measure that is absolutely continuous with respect to the Lebesgue measure, or it could be a singular structure. Well, we can just consider a singular structure, a measure that is not absolutely continuous with respect to the Lebesgue measure, right? So for a singular structure, I actually don't need to erase anything here. I just say that I'm studying this equation in the sense of functions in L2 on omega with respect to some singular measure mu, right? And the singular measure mu is described as the so I start with the periodic medium of with period 1, right? And first define the measure mu. Define the measure mu mu1 as measure mu1 as the for each subset, for each set in R2 or RD. I define the measure mu1 as the total lower dimensional measure of the intersection of omega with the singular structure. And then the measure mu h, should have put one here, so mu h of omega will be h to the d. So I always, so this is h inverse h inverse omega. Is this the right scaling? So we want the we want oh, sorry, this is epsilon, this is not h, right? This is now epsilon. So we want oh yeah, this is right. So this is going to be epsilon inverse omega, and here you have epsilon to the d in mu1, right? So this is how you get this formula. So this is the measure that you are defining now, mu epsilon, and you would like to consider this family of problem with respect to this measure mu epsilon. And well, it's also a kind of homogenization. Well, it is in fact the process of understanding what the continuous medium is that you can replace this original medium with, so that the solutions U, which now depend on epsilon, converge in the weak sense of the energy norm to the solutions of some equation in omega with constant coefficients. So we will be looking for something like this again. And here you see all the information about the measure mu and the singular structure is encoded in this constant coefficients I home. So the process of the passage to the limit and calculating these coefficients at home in this equilibrium problem is well understood, right? But I think in the context of waves there is still a lot to understand, and maybe this is a good point to pass it over to Shane. But I'm sure he will not. He has his own mind about what to talk about today. Okay. Well, thank you.